Have you ever just stopped and wondered how a machine, a hunk of metal and plastic, actually makes a decision? How does it think? It feels like it should be impossibly complex. But the secret behind it all is, well, it's surprisingly simple. So let's pull back the curtain and take a look at the real building blocks of how computers think.
Right, so that's the big question, isn't it? How does a computer choose to do one thing instead of another? How does it handle everything from a simple mouse click all the way up to rendering a photorealistic world in a video game?
Well, it all comes down to the simplest language you can possibly imagine. Every single thing your computer does, no matter how complicated, gets broken down into billions and billions of tiny little questions with only two possible answers: yes or no, on or off. We represent these states with a 1 for on and a 0 for off. That's it. That simple language is called binary.
Okay, so to actually make decisions with all those ones and zeros, computers use these tiny little things called logic gates. The best way to think of them is as a microscopic decision maker. It's a tiny circuit that takes in one or more of our binary inputs, our ones and zeros, and based on a very specific rule, it spits out a single binary output. These little guys are the absolute foundation of, well, everything digital.
So, to really get how the whole system works, we've got to start with the absolute basics. Let's meet the three most fundamental types of logic gates, the ones that are the parents of pretty much everything else.
First up, we've got the AND gate. And honestly, the best analogy is a super strict bouncer at a club or an airport. You walk up and they say, you need your passport and your ticket. If you only have one, you're not getting in. You need both. It's an all-or-nothing situation.
And here's exactly how that plays out. On the left is the symbol for the AND gate. And on the right, you've got what's called a truth table, which is basically its rule book. And look, the only way you get a 1 on the output is if input X and input Y are both 1. Any other combo, you get a 0. No exceptions. Just like that bounce. Next up, meet the OR gate. Now this one's a lot more chill. Think about buying a cup of coffee. The cashier doesn't care how you pay. They just say, you can use cash or credit. As long as you have at least one of them, you're walking away with your coffee. And you can totally see that flexible attitude in its truth table. If you look, as long as either input X or input Y is a 1, the output is a 1. The only possible way to get a 0 out of this thing is if both inputs are 0. Makes sense, right?
And our third basic gate is the simplest, and maybe the strangest of them all. The NOT gate. I kind of like to call it the Bizarro gate, from the old Superman comics. Its entire job is just to do the exact opposite of whatever you tell it. It's a pure inverter. And you can see just how simple it is right here. It's only got one input and one output. That little triangle with the circle is its symbol. And its truth table, it's tiny. You give it a 0, it gives you a 1. You give it a 1, it gives you a 0. It just flips the signal. That's its whole job. All right, so we've got our three basic players, right? And, or, and not. But this is where the real magic starts to happen. The true power comes when we start snapping them together like Legos to create new types of gates. So, say hello to our first combination gate, the NAND gate. And the name is a dead giveaway. It's short for not and. It literally is just an AND gate that does its thing, and then its result immediately gets fed into a NOT gate, which flips it. And you can see its symbol looks just like the AND gate, but it's got that little circle on the tip, which is the universal sign for inversion, or not. Now look at its truth table. You'll see it's the exact opposite of the AND gate. The only way it outputs a 0 is if both inputs are 1. Now, keep this gate in the back of your mind. It's way more important than it looks right now. So, okay, we're building up this nice little toolkit of logic gates, but in the world of engineering and computer science, efficiency and elegance are everything. What if we could simplify things a lot? This is where things get really, really clever. I mean, just think about that for a second. Imagine you're building a huge, complicated piece of furniture. You've got screws, nails, bolts, all sorts of fasteners. But what if you discovered you could build the entire thing just as strong using only one single special type of screw? That's the idea here. Could we possibly build all of computer logic with just one type of gate? And believe it or not, the answer is a huge yes. A gate that has this superpower is called a universal gate. And it just so happens that our friend the NAND gate, that little combo of and not we just met, is a universal gate.
It's the only building block you actually need to build a computer.
Now, I know that is a massive claim, so let's not just take my word for it. Let's prove it. We're going to build our 3 basic gates, AND, OR, and NOT, using only NAND gates. Let's start with the easiest one first.
All right, check this out. Our goal is on the left, a simple NOT gate. On the right is how we make it happen with just one NAND gate. The trick is so simple. You just tie both of the NAND gate's inputs together. So now, if you send in a 1, both inputs get a 1, and the NAND gate spits out a 0. If you send in a 0, it spits out a 1. Boom. It's behaving exactly like a NOT gate. Proof number 1 is in the...
Okay, next challenge, the AND gate. On the right, you can see how we build it with 2 NAND gates. So the first NAND gate does its normal not AND thing. But then we take that output and feed it into a second NAND gate that we've wired up as a NOT gate, just like we did in the last step. So we're taking a not and then we're NOTing it again. The 2 NOTs cancel each other out, and what you're left with is a pure AND function. It's so clever.
And finally, the big one, the OR gate. Now, this diagram looks a little more complex, but the idea is exactly the same. We use 2 NAND gates wired as inverters at the start and then feed their outputs into a third NAND gate. Through some really neat logic, the final output behaves exactly like an OR gate. And just like that, we've done it. We've proven that you can build every fundamental logic component using nothing but NAND gates. Okay, so that's a really cool party trick for engineers, but why does it actually matter? I mean, why is it so important that one gate can do the job of all of them? What does this mean for the phone in your pocket or the computer on your desk? Because of this. This is why it all matters. What you're looking at is a simple circuit called a half adder. It's one of the basic components for doing math. And while it might look like it's made of other gates, remember what we just proved. Every single one of those gates can be built from our universal NAND gate. You combine billions of these simple decision-making circuits, all built from one repeating pattern, and you get a device that can perform any calculation imaginable. And that, right there, is the most incredible takeaway from all of this. All the mind-boggling complexity of modern technology, from streaming a movie to training in artificial intelligence, it's all built up, layer after layer, from these unbelievably simple rules. A tiny gate just decides yes or no, and from that, the entire digital world is born. So, I'll leave you with this one last thought to chew on. We've just seen how a few incredibly simple, logical rules can combine to create something as powerful as a supercomputer. It really makes you wonder, doesn't it? What other complex systems, maybe even in biology or the universe itself, are secretly being run by a set of surprisingly simple, elegant, and fundamental rules?